To begin my presentation, I'd like to provide a brief overview of the objectives and mission of the Fast Reactor Methods program within the Office of Advanced Reactor Technologies. The main objectives for our Fast Reactor Methods program is to focus on the development and validation of computational tools that will support the design analyses of sodium-cooled fast reactors. These focus on several key areas, including neutronics, thermal hydraulics, and structural mechanics. We also look at using tools to integrate these three fields in terms of various systems, such as the reactor core, primary and intermediate coolant systems, decay heat removal systems, in terms of sodium accident scenarios, and containment response. These are done for both normal operation and postulated accidents. By pursuing the enhancement in these tools, we look to raise the technical readiness of sodium fast reactors while supporting their future commercial development. Looking a little bit more into detail of what the Fast Reactor Methods program is looking at, for sodium-cooled fast reactor neutronics, we look at both point and space-time kinetic models, we look at neutron transport, and we also focus on complex reactivity feedback mechanisms specific to sodium fast reactors. These mechanisms include the Doppler effect, sodium density and void worth, fuel-clad axial expansion, and core radial expansion. We also use a wide variety of thermal hydraulic analyses to look at plant behavior during transients and normal operations, and also we utilize computational fluid dynamics codes to look at the effects of very low Prandtl number liquid metal flow and heat transfer. We'll also look at thermal structural analyses tools for core fuel behavior and also for the containment response to sodium fires. Right now, I'd just like to give you an overview of some of the work currently taking place within the Office of Advanced Reactor Technologies for fast reactor methods. We've had a large amount of experimental work throughout the program's history, ranging all the way back to the EBR2 days. And it's important that we archive this information so we may use it to validate future codes. Therefore, we currently focus on archiving this past integral transient data from reactors and experiments from EBR2, the fast flux test facility, and the treat reactors. This next portion talks about specific code activities that we look to enhance to further model sodium fast reactors for their future deployment. We currently utilize the SAS4A and SAS1 system suite, which allows us to do analyses of various accident scenarios, including anticipated transient without scram events. We also look at using the contain LMR code, which is under the MELCORE code suite, and this allows us to support containment design basis assessments with a specific focus on sodium fires. What I specifically like to point out is continued enhancement in these codes and their validation and verification will be strongly considered for this particular call. Now that I've provided you an overview of the objectives, mission, and current work taking place in fast reactor methods, I'd like to point out the specific area of interest for this FY16 call. For FY16, we're currently looking to contributions for the development and validation of reduced order thermal stratification models for sodium fast reactors, with a particular focus with thermal stratification in the upper plenum of sodium fast reactors. In terms of system analyses, we look to use zero-dimensional models. The reasoning for this is while we have done past work with three-dimensional computation fluid dynamic tools, these can be very time-intensive and costly and not very beneficial to full system analyses. Therefore, we're looking to utilize these reduced dimension codes for quicker response times, but also valid outputs to be used for potential licensing applications. Therefore, the main goal of this particular topic is to develop and assess thermal stratification models or to provide the experimental data that can be used for validation of these models. In summary, the primary goal of the Fast Reactor program is to develop the tools to support the design and analysis of sodium fast reactors. This will allow us to raise their technical readiness and will support their commercial deployment. As I've stated, strong consideration will be given to enhancing the codes such as the SAS4A and SAS1 code suites for future use. And for this specific topic, we're looking at further validation of zero-dimensional models for the thermal mixing and stratification in the upper plenum of sodium fast reactors. At this point, I'd like to open it up to any questions you may have on this particular proposal.
Are there any plans to formalize this data into the OECD, an OECD-like benchmark?
At this point, for this particular call, I do not believe this data will be used towards the benchmark at this time, but it could lead to future work for validating these zero-dimensional codes that can possibly play into that in the future.
Is graphite performance also considered?
For this particular area for this particular year, we're focusing more on sodium fast reactor methodologies, so graphite does not generally fall in the purview of sodium fast reactors.
Is there any preference for the software that will be used, such as Moose versus COMSOL?
For that particular question, I know we are generally trying to utilize our own in-house software, which is based off of SAS4A and the SAS1 code suites. To say just based on those two options, I'd say the Moose would probably be the closer of the two, but as I've stated, we're looking for more enhancements upon the code suites currently mentioned in this presentation.
Is thermostructural analysis of containment, including aging and deterioration of concrete shielding, of interest?
That could be an area of interest in terms of containment degradation, yes.
Just to be clear, there is interest in experimental verification of the heat transfer code?
That is correct.
Slide 4 shows the air-cooled RCCS facility at A&L. Can you please clarify the connection of these types of facilities with the scope in RC3?
Sure. That particular facility showed other experimental work that I did not provide a specific example for. That's to show for both fast reactors and for high temperature reactors, that facility is utilized to show possible decay heat removal paths and their effects. So that is how that relates to this scope.
Would access to SAS be available?
That I would have to engage with the technical point of contact on that particular information. There may be an ability for a source code application to be used, but I'll have to dig a little bit deeper for that particular question on a case-by-case basis.
As a clarification, the neutronics have to connect to the stratification issue?
Not necessarily, but what would be beneficial is we're trying to utilize these lower order stratification models for systems integration analyses. So merging that with neutronics would seem to go hand in hand. So it would be beneficial if that were merged.
So the question is, for new software, is it of interest to develop new material models for extreme environments?
I believe just talking about some of the previous questions, referring to materials degradation in terms of containment or accident response, that would be beneficial to have that included. So from that angle, yes.
Are you interested in data taken with high Prandtl number fluids, such as water?
Not necessarily. We're basically looking for low Prandtl number fluids in the liquid metal regime.
To answer the question, do you need further information on the question that they asked? Or?
Yes, that was just what I believe the answer may be. It may be on a case-by-case basis. They can gain access to that particular code suite, but I'll have to confirm with the laboratory technical leads on that to see how you would go about getting a code. I know it is possible, but the exact level of source code or version of that code, I would have to consult with the actual technical lead.
Question you have enough to answer.
Okay, one additional question has come in.
Okay.
Can other metals in place of sodium be used?
For this particular topic of interest, we are trying to focus more on the sodium side. That is what our primary focus of our R&D program is, though other metals would not necessarily be not considered because some may have similar properties to sodium.